Okay, hi everyone, let's get started. So before we start the lecture, here's some announcement about the recording. So all the lectures are recorded. So by default, they are actually in this playlist on YouTube. Right, so whenever Zoom makes a recording available to us, I'm going to upload them, okay? So the raw recording will be there, hopefully, I think like after 24 to 48 hours after the lecture. So the exact kind of time is kind of out of our control because that depends on how fast Zoom make it available to us. And for every single lecture, after I upload them into the playlist, you can already access them, okay? So, and then I will send out an announcement on Moodle for each lecture after I have done the following. Okay, so I will, you're going to receive an email like this, right? So I will do a quick proofreading of the subtitle and the captions and do a little bit of refinement if necessary, right? And you will know I have done it because like if you like look at the subtitle folder for each of the video, you can see there is like one that's English but not English auto generated. Like when you see this thing, yeah, so you will know that I have done my pass, right? But even before I do it, it's going to be in a playlist. So I will organize a video into different chapters, right? So you are going to see it in the description section of the video once I have done it, right? So you can actually jump around to different part of the lecture, okay? So this step took time, right? So that's why there's going to be a gap between when I kind of upload the video, make it available in playlist, and I send out the announcement after I do my refinement. Okay, so one example is lecture 2, right? So it's right now on YouTube. You can actually see it in the playlist, but I haven't finished my pass, so you haven't received the email like the announcement on Moodle, like on Moodle about where it is, right? But you can still access it, right? You can just go to the playlist. So if you want to watch the raw video, right? So you can just check the playlist. It already have automatically generated subtitle. There's no chapters, but all the content are already there. Actually, the automatic generated subtitle is actually pretty good in most cases. So otherwise, if you want to see all the chapter type of thing, you can wait for the announcement on Moodle. There will be a delay, but we will try to control the delay such that it's shorter than a couple of days, right? So I think hopefully lecture 2 is actually kind of one outlier that like about that. So, and on the other hand, if there's anything that we can do to help you kind of to learn the content of this course, please let us know, okay? Okay, so let's start. So what have been talked about in the last lecture, right? So in the last lecture, we actually get into a little bit about how to model our knowledge about the world and also how to essentially model the data, right? So which is one representation of the knowledge. So we start from relational model. That's actually one way of modeling data and knowledge that we are going to focus on in this course. So, and we start from probably one of the most natural way to model facts and the knowledge, right? So that is by organizing them into something that is very similar to a table, right? So you have a table, and then if you observe the structure of this table, there are different columns, different attributes, right? So, and there are different rows, right? So each row corresponding to maybe one entity, right? In the table, and each column corresponding to some attributes of that entity. And we formalize this a little bit by defining two things. We first define what is a schema in a relational model. So a database schema contains a set of schemas for different relations. And for each relation, the schema contains the name of the relation and also a set of attributes or columns, okay? And then it's also come with a primary key that we talk about it. So for each field or attribute, it comes with its name and also a domain that it can take value from. For example, integers or strings or floating point, so on and so forth. So here's just one example, right? So if you give me a relation schema look like this, the name of the relation is students. It has 5 attributes: student ID, the name, the login, the age, the GPA. And here, by underlying this attribute, we say it is actually a primary key, which means that if you give me the value of student ID, I can uniquely identify one row in this relation. On the other hand, it means that I cannot find two rows in this relation that share the same value of student ID. So when we talk about schema, we are not talking about the content that you put into that relation. You can think about that as pretty much a header of the table, tell you the shape of the table, tell you what type of value I can put into each cell. It doesn't contain the content, it only contains the header. So I think someone raised their hand. Yeah, go ahead.
Yeah, sorry. So this has nothing to do with the thing that you're talking about right now. But in the chat, there's some confusion about when the exercise sessions start, because I think in the slides you said in the third week, which would be next week. But in Moodle, we got an announcement that they start this week. So the question is, do they start this week or next week?
I don't think it's going to be this week, right? So so let me check with the. Okay, so for the exact day, let me check with Ingo, the head of TA, like about that. But I think we released the exercise. Okay. So I mean, there's a release of the exercise that you can actually work on it, and then there's an exercise session. Maybe there's some confusion there. So we are going to send an email after the course, like to clarify it. Okay.
Okay. Thanks.
Yeah. Yeah. Sorry for the confusion. Yeah. So. Okay. Yeah, let me keep notes and then I can remember. Okay. Okay, cool. Yeah. Yeah, so this is the schema of the relation, right? And then we also define what is a relation instance, right? So an instance in the relational model is pretty much the content, right, of all those kind of table-like relations, right? So specifically, if you give a relation that looks like this with the name R with n different attributes, f1 to fn, each one have the domain from kind of d1 to dn, right? So an instance of this relation is really a set of tuples, right? So it is actually a subset in this cross product of domains, okay? So intuitively, you can think about an instance as a content of relation, right? So if you think about a relation as a table. So here's one example that we looked at before. So I have this relation containing information about students. This is one instance of this relation. You have 3 different rows, and then you have the concrete value for each of the attributes for each of the rows. So whatever you put into this instance need to respect the domain constraint, right? For example, you cannot put a string in the column GPA because in the domain we define that as floating point. So one thing that we need to keep in mind is in relational model, we always assume we are talking about the instance as a set of tuples. So there's no duplicate tuple in relation because it's a set. And also the order of how you write down those tuples doesn't really matter. In reality, when you talk about the real database system, there are some differences. For example, most of the database system will model a relation as a bag of tuples. There could be duplicates, right, instead of a set of tuples. But when we talk about relational model in the course and also in the exam, we are always thinking about as a set of tuples because that makes our life much easier. So, and we talk about a little bit like other type of concept, right? So you have the schema of relation R, and one very important concept is the notion of key, right? So a candidate key is a minimal set of fields or attributes that can identify each tuple uniquely, okay? And then among all the possible candidate keys, you can pick one and use it as primary key. Every single relation need to have a primary key. So it is always possible because relation is a set. In the worst case, you can use the full set of attributes, right, as a key if you cannot find a smaller subset. So this is one example, right? So I have student relation, I have SID, The underline means SID is the primary key, right? So if you think about what this concept of key is trying to do, it's really try to define what type of instance is valid and what type of instance is not valid. This is one example of a valid instance, because if you take any of the two rows in the relation, they will not share the value of SID, which means that if you give me the value of SID, I can uniquely identify one row in the relation. That's what we are trying to convey by saying that SID is a primary key. Okay. This is one example of an invalid instance under the current key constraint. So here you can see the first two rows, they share the same SID value. It actually violates the key constraint. And we talk about it in a more formal way, right? This is actually all the valid instances that is allowed under this key constraint. You can check that in a very precise way. And this is just one way to define all those constraints that we are allowing in the relational model. Down the road, a little bit before Easter, we are going to talk about different ways of introducing more type of constraint into our relational model. Okay, we talk about relational model and we talk about relational instances, right? So we talk about key constraints, and we also talk a little bit about how to get insight and information out of data modeled in a relational way. And we define query as a function that take as input a database instance and output a new relation instance. There are different ways that you can design a query language. And we talk a little bit about how to do that in relational algebra, which essentially treat each relation instance as a set of tuples and use set operations to manipulate them. So in this lecture, we are going to talk a little bit beyond relational algebra. We are going to talk about different types of query languages. Specifically, we are going to talk about relational calculus, and then we are going to compare relational algebra and relational calculus. And as we will see, relational calculus is actually slightly more powerful than relational algebra. And we are going to talk about different types of query languages and their relationship. And if I have time today, we are going to go to the practical side, right? To think about how to actually write some of these queries in a real world database system. And we are going to talk about this practical query language called SQL. It's important for us to do the theoretical part first, because then you can see the almost one-to-one correspondence between what you are trying to write in a practical database system and what we have on the theoretical side. So in this lecture and also in the next couple of lectures, we are going to work on this diagram. We are going to go through every single query language, and we are going to understand the pros and cons and the constraints and limitations of that query language. And we are trying to understand the relationship among these query languages and also how to write it in a real world database system. That's what we are going to do. Okay, so this is a long list of agenda. We are going to wrap up the relational algebra part in the next maybe 10 minutes, hopefully. And then we are going to talk about relational calculus, and then we are going to go through different type of query languages. Okay. So let's just refresh our mind about relation, like relational algebra. Okay. So essentially, it is an imperative. It's an imperative way of querying kind of database, in the sense that you tell the database how to get the answer that you want. It treated relation instances as a set of tuples, and it try to query it using set operations. And in last lecture, we talked about a whole bunch of operations that you can do, right? We talk about the spatial operator like union, difference, selection, projection, cross product, renaming, and joins, right? And then let's look at one example, right? So this is the student database that we have. You have professor, student lecture, requires, right? All those type of information. And if you want to ask the query to say, okay, so let's try to find the course that the student cannot take because they fail to pass the prerequisite, okay, the direct prerequisite of that course. So how would you represent this query using relational algebra, right? So let's look at what relation that we need to get the information from, right? We need to get the information from the student relation, right? We need to get the information about kind of the prerequisite relation, right? So like which course depends on which one, right? And we need to get information about the test relation, right? To see whether the student passes the courses or not, right? So one thing we can do is we can have the natural join between student and test, right? And that will actually give information about which student take the test of which lecture and what is the grade, right? And then we do one selection operator to filter out those tuples with grade smaller than 4.0, right? So in this database instance, it's going to give you this single tuple, okay? And then we are going to have another layer. We are going to join the result of this, right? So this tuple, like this relation instance with a single tuple, with the requires relation, right? And to get essentially all the courses whose prerequisite is 5001, right? Because 5001, right? So it's a course that these students fail. Right? So it's going to give you something like this, right? And then you do one kind of projection to get the student ID and the follow-up course, and you get something like this. Essentially, this very long expression is the relational algebra kind of a representation of the query that you want to ask the database. And as you can see, the database system could follow this expression step by step and give you the answer that you want. Okay, so this is just one example about how to write relational algebra, kind of like to answer the query. Okay, so let's look at the property of relational algebra, right? So one thing that's very important is to keep in mind that relational algebra is not declarative. What do we mean by that? What we mean by that is there are different ways for you to implement the same query. Okay, so let's look at one example. If you want to get all the students who took database course, so there are different ways for you to write it down, right? You can first have the natural join between student and attend, and have then you have natural join with lecture, right? And then you do the selection and the projection. But you could also do for example, the cross product between student and lecture, and you do the natural join with attendance, right? And then you do the selection and the projection. Both of these queries will give you the same answer. They are essentially equivalent under the current relation schema. But the difference is that they are going to have very different practical performance in the sense of like speed. Because to calculate this cross product, it could be very large. If you have 1,000 students and 1,000 lectures, the result of this cross product is going to be 1 million rows, right? Because it's cross product, right? So these two different ways of implementing the same query is actually having very, very different performance. And that's what we mean by relational algebra is not really declarative, because the user is really need to decide which way to tell the database to run, right? So in real world database systems, we actually do not want the user to write relational algebra because of this. What we really want is to have a query language that is declarative, which means that the user doesn't need to worry about different ways of implementing the same query. We want to make sure the user tells us what they want, and then we automatically generate relational algebra expressions to get it done. So that is our goal. And that is why in practice, you are not writing relational algebra in database that frequently. So let's also look at one limitation of relational algebra. We talk about so many different queries that we are able to write using this language. But let's also look at examples that we cannot write in relational algebra, okay? So look at this query. We have the parent relation with two attributes. The first attribute is the parent, the second attribute is the child. And the query I have in mind is like this. I want to find all the ancestors of B. Okay. So how can I implement this in relational algebra? Well, I mean, if you want to answer this query, we kind of need to go up from the bottom to the top in a family hierarchy, right? So you can write one expression to find all the parents of B, right? So how can you do that? It's actually very simple, right? You do one selection on the parents relation, right? And then you subselect all the tuples with the child attribute equals to B, right? And then you project to parent. And then essentially you can get all the parents of the person B. And then I can get the grandparent of B, right? I just go one level up in the hierarchy. So what you can do, right? You can actually join the parent relation with the parent of B relation that we just get. And then you can actually go one level up. And you can keep doing this. You can get the great grandparent of B, right? But just keep doing this type of joins, right? Every single time you join it once, you go one level up in the hierarchy. But the problem is that it will never end. That is, I cannot have a single relational algebra expression that allow me to get all the ancestors of B for any database for all the database instances. Why? Because I don't know when to stop. If you think about all the operations that we have been introducing so far, there's no for loop in relational algebra, right? So we cannot write a for loop here, right? So essentially, one fundamental limitation of relational algebra is it cannot handle this type of recursive structure. Okay, so when you are using this, just keep that in mind. That's a pretty fundamental limitation. Later in this lecture, we are going to see in practice how you are going to implement those recursive queries in a practical database system, right? But then we are going to essentially like introduce some pretty fundamental change over the relational algebra kind of abstraction that we are kind of have been looking at so far. Okay. So one thing that we need to realize is that we talk about relational algebra, right? So in a database course, but the impact of relational algebra actually goes beyond database. So even though practical database system it's not often that you write relational algebra because it's not declarative. In practice, in some other data systems, you are able to write relational algebra and actually quite frequently. Okay, so especially if you are using some modern data analytics framework, it actually gives you a way to write relational algebra expressions. Now we are going to look at one examples about how you can do that in pandas or when you are using data frame. So this is just a demo, right? To make sure you kind of understand, in practice, people actually do this, right? It will not be in the exam, but I think as a kind of undergrad student at ETH, we will be really happy if you know about it, right? So we will not test Python, we will not test pandas, we will not test data frame, but I think it's important for you to know you are able to do it. So let me... Yeah, so this is just one example, right? So you can find the link like on our website. So once you can do in pandas, right? So it's actually you can define something called a data frame. Okay, it's very similar to a relation that that we have been introducing in the course. This sounds like different that we are not going to talk about. So essentially, you can think about each of this as one attribute. Okay, so you first define the key and you put the value there, K0, K1, K2, you can put whatever you want, you can put the rabbit there, right? So, and there's attribute A, there's attribute B. If you do this, essentially you are going to define kind of a table that looks like this, right? With 4 different rows and 3 different columns, right? Something like this. Now you can define a different data frame that looks like this, right? With the name B. And then there's 4 different rows and 3 different columns, and you can put a dog here, right? Whatever, it's just a string. And you can actually have those like heterogeneous data type, for example, here, and put in kind of integer instead of string, right? So, and it's, the system is okay with that. Okay. So, and then you can actually introduce a whole, like implement a whole bunch of like relational algebra expression that we have. For example, you can actually write down those kind of subselection. Right? If I want to select from B, where the value of the C attribute equals C0, right? So one thing you can actually do is actually you can actually write something like this. You define the filter function, right, to that return true if and only if the tuple has the attribute C equals to C0, and then you can just put it here, right? If you run it, it's going to sub-filter like essentially this kind of like single row, right? And you can do projection. It's also give ways to do projection, right? And then you can actually put them together. You can first do selection and then do projection, right? And then you can actually do join, right? So the only difference is that if you have a relation A look like this, relation B look like this, the name in pandas is they actually call that merge instead of join. But if you look at the result, that's pretty much the same thing, right? So it's going to take A, right, and take the key attribute, right? And for K0, it's going to find another tuple in B with key equals to K0 and return it, right? So you can find it for K0, so there's one tuple here. You can find that for K1, so there's another tuple here. You can find K2 is fine. Rabbit and dog are different, so it won't appear in the result, right? So as you can see, this is pretty much just giving a different name for the relation algebra expression that we have, like talk about, right? Like in this course, right? So in practice, you are able to do many of those operations that we have been talking about in those data analytic systems. Okay. Yeah, this is just one example about where you can see relational algebra kind of in practice, because you are not going to write that frequently in database, but you are able to write it in other type of data systems. Okay, this is the basic of relational algebra, right? So then let's look at some of the extensions. Okay, so we talk about that when we talk about the relational model, it's always our set, right? But you can actually extend the whole system to deal with a bag of examples. Okay, so and that's actually makes things a little bit more complex, and we are going to actually see a couple of examples here. So here, let's assume each relation is a bag of tuples. They are not set, they are bag of tuples, right? So which means that you could have duplicated tuples in the same relation. For example, when you're dealing with set, I have a tuple 1, 2, 3, right? But when I talk about the bags, right? So I could have multiple instances of 1, right? So here I could have 3 of the 1s, right? I have 2 of the 2s, I have only 1, 3, okay? So you cannot have this when you think about relation as a set, right? But when you think about relation as a bag of examples, you could have that. So when you really extend a relation from set to bag, it's getting really complicated because extending relational algebra from set to bag is actually non-trivial, okay? So we are not going to go really deep into this. Whenever we talk about relational model in exam, we always say it's a set. But I want to show you guys kind of some caveat that we are going to have if you really want to do relational algebra over bags, okay? So what are the differences? One difference is that the semantic of the operator are going to be different. For example, if I want to union two bag, you need a different semantic compared with union between sets. So here just one example. Assuming I have two bag of tuples, the first bag is I have 2 1s, and then I have 1 2, okay? And then in the second bag, I have 1 2 3, okay? If you do union between these two bags, the result will be look like this, okay? You are going to have 3 appearances of 1, 2 appearances of 2, and 1 appearance of 3, okay? It's going to be different compared with like doing that over sets, right? Because now I need to take the count of all those examples. And similarly, if you want to do the differences between two unions, it's going to be different. For example, here I have 2 appearance of 1 in the bag. I have 1 appearance of 2 in the bag. If I want to calculate the difference between this bag and this bag, right? So I still have 1 appearance of 1 left. Okay, simply because I have 2 ones here, I have 1 here, right? So in the result, I will still have 1 left. So that's actually different from this type of operation over sets. And also, what's more interesting is many of the laws that govern the operations are also become different. So here's just one example. Okay, so when you have the intersection between R and this sub-expression, right, which is a union between S and T, if you are doing this over set, the operation, the expression on the left-hand side is actually equivalent to the expression on the right-hand side. However, if you are doing that over bag, they are actually not different. Sorry, and they're actually like very different. They're actually not the same. So just look at one example, right? So think about you have this case. I have 3 bags. They are the same. R equals to S equals to T, and they have 1 appearance of 1 in each of those. So, and then if you kind of write down kind of the result, you are going to see this is going to be one counterexample showing that if you are doing this over bag, the left-hand side is going to be different from the right-hand side. If you are treating R, S, and T as set, you are going to see that the left-hand side is going to be equal to the right-hand side, okay? So essentially, when you kind of extend relational algebra from set to bag, the laws governing those operations are also become different. Right? So, and also you need new operators, right? Because now I could have duplicates in my bag, right? So people often introduce a duplication elimination operators, right? To actually remove all those duplicate tuples or examples, right? So that makes the thing a little bit kind of more complex. And apart from the extension from set to bag, right? So in practice, right? So you can actually also extend relational algebra, right? By introducing other operators, right? So the thing that we have been talking about in the course is only a small subset of what you can do in relational algebra, right? So you can introduce the sorting operations, right? To sort all those tuples, right? Translate a set into a list, right? You can have group by and aggregations, right? So in relational algebra. So we are not going to talk about that like in this course. But it's important for you to know you are able to extend relational algebra by introducing more and more operators. Okay. Okay. So that's relational algebra, right? So now let's switch gear and try to understand another query language and compare that with relational algebra. So we have seen that relational algebra actually queries the data in an imperative way. Okay, you are really giving the system one expression such that if the system follow it step by step, you are able to get the result that you want. Now let's look at a different query language that is declarative. Okay, so and the fundamental idea is to use mathematical logic as the way to declare your query. So what do we mean by that? Essentially, we are going to treat each relation as a logic predicate. And we are going to think about a relation instance as a collection of facts. So essentially, if one tuple appears in a relation instance, for example, here I have the tuple 0, John Zurich, right, in the customer relation instance. What we mean, like how we think about it, is that we have this logical expression evaluate to true. Okay, so this is just standard notation in first order logic. Okay, so this is how we think about relation right now. Okay, now we think about relation as a collection of facts. So what do we mean by that? What we mean by that is if one tuple appear in this relation, it means that if I think about relation as a logical predicate, then this thing is going to evaluate to true. Okay, if you think in this way, the power of this is now you can express your query as a first order logic formula. So here's one example, right? So if you think about relation as this, you can actually write down a set defined by this logic formula, right? So essentially, you can say, okay, so what is the information I want to get out of this database? I want to find all the product ID and the customer ID tuples such that this formula evaluate to true, which means that there exists a value of variable like n and p such that this thing is true, this thing is true, and this thing is true. Okay, if you think about the relation as a logical predicate, you are able to write a query that looks like this. It's actually equivalent to a formula look like this if you treat each relation as a set, right? So here I want to find a PID and a CID such that there exists N and P, that PID and P is in product, right? So on and so forth. Once we think about relation and as logical predicate, we are able to write a query that looks like this. And this is what we mean like by domain relation calculus, okay? So what is the answer of this query, right? If you look at this query, what is the answer? The answer of this query is simply this set, right? It's all the PID and the CID tuples that evaluate to true, okay? So, and it's actually easy for you to see that this query is going to get the same result as the following relational algebra formula, okay? So when you go at home, you can actually try to put these two queries side by side. And you can understand this query by just going into the definition of of this set, right? And then you can actually see this query defined in relational calculus is actually going to give the same result as this relational algebra expression. Okay. So now let's define this in a more formal way. So we define the schema of database as follows, very standard. A database schema S contains a schema for different relations. And for each relation, the schema is defined by the name of the relation, here's R, and also a set of attributes, here A1 to AN. Each of them has a domain, which is D1 to Dn in this case. And we define domain, right, as the union of all the domains of the attribute, which is pretty much all the values you can take in the database. Okay, so this is kind of infinite set of constants that you could take in your database, which is the union of all the domains of the of attributes. So what is the database instance, right? So database instance of R is simply a subset of the cross product of the domains. For example, here, if you have relation R, right? So one instance of this IR is a subset of this cross product, right? So I have n columns, right? So I take the domain and cross product n times, right? For every single tuple in this cross product, right? So that can be in some of the instance of this relation. So one thing that is very important is for database, we always assume an instance is finite, okay? So an instance of relation R is a finite subset of the cross product of the domain, right? How many times do you cross product it, right? So that equals the number of attributes you have. And database instance, right? An instance of a database is actually a function I that actually map each of the relation, at least a name, right, to its instance. Okay, so here you can think about each Ri as which is the name of the relation, right? So a database instance is simply a function I that actually map this relation to its relation instance. Okay. So an instance of relation is a finite set of facts over the relation. An instance of database is a finite set of facts over all the relations. Okay, so like formally, this is essentially what we are talking about. Okay, so and then given this, we can actually formally define a relational calculus query that looks like this. So essentially, let's try to define the syntax, and then we define the semantic. So syntax is as follows. You can give me a first order logic formula phi with three variables, x1 to xk. Okay, and then given that, I can construct a relational calculus query q phi that look like this. I put all the three variables here, and then I put phi here. Okay, so this gives you a domain relational calculus query. And if you look at this concrete example, right, so you can see this formula, right, is a first order logical formula, right? And then it has two free variables. Your PID is free and CID is free, right? And you put them here, okay? So this gives you a domain relational calculus query. So what's the semantic of this, right? Let's define the semantic. You give me the query. What is the answer of this query, right? So the standard semantic here is that we think about each relation R corresponding to a predicate R in this formula, okay? And we think about each database instance corresponding to the standard first order interpretation, right? And then we think about assignment in the traditional way, okay? So as the mapping from variable to a constant in the domain, okay? So given this, the answer of the query Q is simply defined by this. Essentially, that's all the possible assignment of the free variable. Here, essentially, all the assignment of the free variable such that the intuitively, right? So this formula phi evaluate to true given your interpretation and given that assignment. This is the kind of the formal definition about the semantic of a domain relation calculus query. Okay, as you can see, there's a very close connection between what we are talking about here and what you were learning maybe last year in your kind of mathematical logic course. Okay, but there are caveats. Here, essentially, every single answer, every single model, right, in the traditional sense, is finite, right? So we only care about the database instance that is a finite subset. Okay. So given this, right, so let's look at some examples. Right? If I have a relational calculus query look like this, I want to say, okay, so is the tuple 0, 0 in the answer? So in this case, you can actually do a pretty kind of mechanical exercise to know the answer, right? So here, yes. Why? Because I can find an assignment to replace PID as 0, N as iPhone, P as 110, and CID as 0, CN as strong, right? C as Zurich, and X equal A, and I just put them all into this formula. It's going to evaluate to true, okay? And which means that, okay, then this assignment is going to give me an answer, and that assignment is going to put PID as 0 and CID as 0. It's as simple as that, okay? So similarly, you can say, is the tuple 0, 2 in the answer? Here is actually no, right? Because you simply cannot find that assignment. So this is a very formal way to define relational calculus. And essentially every single time, as you will see, whenever you are writing a SQL query, the beauty of database is you are writing a logical formula like this. However, you are not going to realize it when you are using a real world database system, right? And the beauty of database is really give you a way that's very easy and very, very high level type of language for to specify this very precise logical relationship between input and output. And as a user, you don't really know this, right? But it's very important for all of you actually to know underneath the cover, this is what database is trying to do, okay? So let's take a break. I'll be here to answer your questions. When we get back, we are going to continue to talk about relational calculus. Okay, if you have any questions, just raise your hand. I think there are some questions. Right. Yeah, go ahead.
Okay, so I have two questions. So one would
Yeah.
be so an assignment is a mapping alpha from var to the domain. So
yeah.
What is var referring to? Like, is it the free variables here, or like we didn't read?
Oh yeah, that's a good. Yeah, so var is all the free variables. Yeah, it's a set of free variables. Essentially, like assignment is a mapping that if you give me a free variable, I give you the domain. Sorry, I give you a constant in the domain.
Okay, and then the instance, if we think about it in the first order, is this just the universe, or what exactly is it? Because I have like on the slides before where you defined I didn't quite understand the function. Like, what does it mean that it maps Ri to an instance of Ri?
Oh yeah, okay. Yeah, so here a little bit confusing. Okay, so it's clear what the instance of R is, right?
Yeah.
Okay, so I'm going to talk about database, right? So you have multiple relations, right? So here you have R1 to Rm, you have multiple relations. So this I is simply tells you, if you give me relation Ri, I'm going to give you an instance of Ri. If you give me the name of Ri, like student, this function is going to return like an instance of that student.
I see. Okay.
Yeah.
Okay.
Yeah. So it's very simple. Yeah. So, but if you want to go like formulate, this is actually what it is. Yeah.
Okay. Thanks.
Yeah. Yeah. Go ahead. Yeah. You can just unmute yourself and speak up.
Hello.
Hello.
Okay. I have two questions, not about relating to this lecture, but last lecture actually.
Okay.
One of them is, what happens when you use a projection on a relation and you don't mention the key, so you don't list, let's say, the primary key? Is that even legal in the semantics of, like, for example, SQL or something?
Okay, so let me rephrase your question to make sure we're on the same page, right? So your input, you have a relation for which you do not have primary key, and then you do projection on it, or
no? You have like a schema or a relation which has a primary key.
Yes.
And then let's say you have like student ID, name, and I don't know, course.
Yeah, sure.
Right, and and then you do a projection on it, and you just the primary key is obviously student ID, and you just project on.
Oh, okay. So essentially, you just project out the primary key, right? So that's essentially your question. Yeah. So so like in that case, your question is whether that's legal or not, right? Yes, that's legal, right? In the sense that and if you do not specify essentially the primary key of the output, right? So in the worst case, I can always use all the attributes as a new primary key of the output, right?
Okay, makes sense.
Right. So and also that's in theory, right? So like in practice, in a practical database system, yes, I mean it won't stop you from doing that. Right. Yeah.
Okay, makes sense. And then my second question is, I don't know how long this will take, but would you mind explaining again like what a semi-join is? Because I didn't quite understand, like, from the lecture and in the book they never talked about a semi-join either.
Yeah.
Like,
oh yeah. Yeah, so can we keep that question like toward the end of like essentially after the course we can we can talk about it. So is that okay? Yeah.
Wait, what? Sorry, what?
Yeah, so like can we do that after the lecture? Yeah,
of course,
do the semi-join.
Sure.
Yeah.
Sure, no worries.
Yeah, because that probably take more than a couple of the minutes. Yeah.
Okay. Sure.
Okay, but I will be here, right? So you can ask the question again, and we can go through that. Yeah. So actually, if you look at the last lecture in the QA session, after the lecture, I actually go through one of the semi-join examples, Yeah, but we can go through that again. Yeah.
Okay, if it's like I never actually looked at the Q&A. I left a bit prematurely last time. I'm sorry.
Oh yeah, yeah. But it's available in the recording. Yeah.
Okay, sure. Like in that case, I'll just look at that and then.
Yeah, perfect.
mean,
yeah. So
If
yeah.
you
So
would say if you would say you explain it again there, then there's no point in me asking that question again.
yeah, I'm not sure whether that answer your question. That's going to answer your question, but if it doesn't, just ask again. Okay.
Okay, I will do. Thank you.
Perfect. Yeah. Yeah. Go ahead. Go ahead. I think there are more
I
questions.
also have a question.
Yeah.
Sorry. Am I okay? Maybe it's also a question that you want to answer after the course, but would you mind to explain me how the hierarchical model is implemented? So especially the yellow parts, are they tables or are they objects? And how are the edges implemented actually in the implementation of a hierarchical model?
Okay, so let's do that after the lecture. Yeah, so if that's okay, because I need to switch the slides to the first lecture, right? So can we do that after the lecture? Yeah.
Yeah, sure. Yeah. No
yeah,
problem.
perfect. Yeah. Yeah. So you have any other question that speak up? So I won't be able to see the chat. Like that's too many messages in the chat window, so I might miss your question if you just type in the chat window, right? So if you can speak up, that'd be great. Yeah.
Hello, can I ask another question?
Oh, sure. Go ahead.
I don't know if I remember it correctly, but I think that right before the break, you mentioned something about the main relational calculus being used under the hood of most database systems. And I didn't really understand what you said there. So maybe do you want to explain it for me again, or like shortly what you meant with it?
Oh yeah. So we are going to see one example maybe later today or on Friday, right? So essentially, so if you are using a database, right, you are using a SQL query, right? So as we will see, it's actually something that's very similar to natural language. You actually select something from this relation where this predicate is true, right? So that's actually what you are writing as a user of a database system, okay?
Yes.
So every single query you are going to write, well, yeah, so yeah, SQL is a complicated thing. So for many of the SQL queries, right, that we are going to talk about in this course, there's a one-to-one correspondence between that SQL query and the relational calculus formula.
Okay.
And essentially, when you are using database, right, you are actually writing relational calculus formula. But as a user, we actually abstract it from you such that many of the users don't really know what they are trying to do, right? So that is actually like what I mean. Yeah.
Okay.
So it's going to become very clear when we look at a concrete example about the connection between the SQL query you are writing and the relational algebra formula and the relational calculus formula.
Okay, great.
There's a
thanks.
very beautiful equivalence between these three. Yeah.
Great.
Cool. Yeah, go ahead.
Yeah, so I was thinking about the first order logic. So the predicate is the relation, right? We said the relation is the predicate of the first order logic. So is there an equivalent for functions defined in the relational calculus?
Oh, that's a good question. That's a very good question. If you're talking about the full database theory, okay, so if you read the Alice book, that's like 400-page book, you are able to define functions. Yeah.
But it's not relevant for the, so we didn't mention it on this slide, so I didn't miss anything.
That's true. So
Okay.
here we see, so here we don't deal with that. Yeah.
Okay, good.
So like in principle, you can have later you're going to see like conjunctive query with function symbols, right? So that's a different thing. Yeah. So that's going to take the whole semester to understand that. Yeah.
Okay. Thanks.
Yeah.
Excuse me, can I ask a question?
Oh, sure. Yeah. Sorry, I was away for 1 minute. Yeah, grab some water. Yeah, sure.
Yeah, no
Go
problem.
ahead. Yeah.
I wanted to ask because I actually got that question in when we got first order logic in formal methods and functional programming.
Yeah.
And my question is it syntactically legal to have a variable bound by two quantors? So for example, for all z exists z, where z is a variable.
Oh, I don't think so, right?
So every variable can have maximally one quantor that bounds it.
I think so, right? So yeah. So
Okay.
Yeah. So essentially one variable can only bound it once, right? So otherwise we don't really know what that is, right?
Okay, thank you.
Yeah. Yeah. So yeah. So like of course. I mean, and that depends whether what do you mean by variable. Whether, for example, whether the same name can appear twice, right? For example, you have nested structure, right? So of course, the same name can appear twice, right? But
yeah, I just mean that, for example, if you got for all z exists z, then the variable z is bound by the exist, but also by the for all quantifier.
oh, this cannot happen, right? Yeah.
Yeah. Okay.
Yeah.
Thank you.
Sure. Okay, so let's get started. Cool. Yeah. So we talk about relational calculus, and you can see the connection between the query language we have with mathematical logic, and that's really the beautiful part of database. I'm very excited about that. So now let's look at this in more detail. Okay. So let's try to understand the following kind of fundamental question. If I give you a relational calculus query Q phi defined by the formula phi with free variable x1 to xk, is the answer always finite, right? Because we are building database, we want to make sure our answer is finite. Otherwise, we are going to spend the rest of our life outputting stuff to the user, right? So this is actually a very fundamental question in database. You give me a query. Is the answer of this query always finite? So it's no, right? So you are able to construct a query with an infinite answer. So what do you mean by that? Let's look at one example, right? In this very simple schema. I have a query look like this. The free variable is PID, name, and price. And my formula phi is very simple. It simply says that the PID, name, and phi is actually not in this product relation. That's essentially what we are trying to convey using this query. And let's think about in what scenario that this query is going to give you an infinite answer. So think about you have an empty database instance, okay? And then what would be the answer of this query? Well, the answer of this query would be the full cross product of domain, right? So if you think about why is every single assignment of PID and name and price, right? So they are going to satisfy this formula when your database instance is empty, right? Because my product relation has nothing, right? No matter what value assigned to PID, to name, to price, they always satisfy this formula. So they should always be in the answer. In this case, this is a very simple example of a relational calculus query that are going to get infinite answer over a finite database. If you think about it, it's quite surprising, right? So the fundamental reason behind it is actually your domain is infinite, right? So and your answer to the query is going to be infinite. So that's actually not something we want in a database. Right? Think about you are the builder of a database system. You want to make sure whenever user give you a query over your database, you want to make sure the answer that you have for the user is at least finite, right? Otherwise, you are setting yourself up to failure because, I mean, there's no way you can give the user like infinite amount of tuples as the answer of their query, at least in the generic case, right? So we need to understand a little bit about how to constrain the set of queries that we are allowed to ask in a database system. And there are actually two ways that you can kind of twist our definition of relational calculus such that you can at least understand whether the answer will be finite or not. So here we are going to talk about safe queries and unsafe queries. And we are going to provide a very precise definition down the road. And we are going to talk about something called domain independent relational calculus, which is actually the safe semantic for queries, which is going to always return a finite answer. Okay, so let's talk about the safety of queries. What do we mean by one query to be safe? We say a query Q phi is safe if and only if this query going to give you finite answer over all possible database instances. Okay, so let's go through some exercise, right? So is this query safe, right? So I have X, and then my formula is actually not Rx, right? So this query is not safe, right? Why? It's actually the same reason as what we had before, right? So you could give me an empty database instance, and then this query X, every single constant in the domain should be the answer, because domain is infinite. I'm going to have infinite number of tuples in the answer. Okay. So similarly, whether this query is safe or not, if you think about it, right? So my free variable is X, right? So I want to say, oh, exists Y such that this is true, right? So you can go home and actually try to think about it. This query similarly is also not safe. And this is another 2 more examples of a query that's not safe. Okay, so when we go back home, try to think about it. Right? It's kind of very natural and easy for you to reach the conclusion that all of these 4 queries are actually not safe. So if you give me a query, right? Because now we have the notion of a query being safe or not. So a very natural fundamental question that we can understand is really that how hard it is to decide whether a query is safe or not, right? So that's a very natural question. So one problem is that if you take the view, I mean, if you give me no constraint on what type of query I can write, if I'm able to write force-out logic queries, deciding whether that query is safe is actually not decidable. So we are not going to go to the detail about how to prove it. If you really want to prove it, it's a reduction from force-out finite satisfiability, right? So, but essentially in general, if you give me a force-out logic query, deciding whether it's safe or not is undecidable. So that's the property that we really do not want. If I am going to build a system, I really want whatever query you give me, at least I can tell you that's safe or not, right? So what can we do? So there are 2 things that you can do, and we are going to look at them one after the other. The first thing that you can do is you can actually constrain your syntax. You can actually say, okay, so you cannot give me a force-out logic formula in general. Here's a subset of syntax that I allow you to write, such that it's always safe, or I can decide whether it's safe or not in a finite amount of time. Another thing you can do is to redefine the semantics. I still allow you to give me the same type of queries in force-out logic, but I'm going to define what do I mean by the answer of that query. We are going to look at these 2 aspects, one after the other. But let's look at the semantic first. So what's going to get us is something called domain-independent relational calculus. So if you think about the fundamental reason about why some queries could be unsafe, one of the reasons is actually the answer of that query is actually dependent to your domain. What do I mean by that, right? It means that, so think about the query that we had before, right? So you have X and the condition is not Rx, right? So in that case, your answer, right? If your R is empty, it's a function of the domain. If the domain is infinite, you have infinite tuple in your answer. If the domain is finite, you have finite amount of tuples in your answer. And we call those type of queries whose answer depends not only on the relation, but also on the domain, domain dependent. And one thing that we hope to do is to turn a query, relational calculus query Q5, into something that's domain independent, in the sense that the answer of this query is always a function of the interpretation of the relation, which is the relation instance, but not the domain, which is infinite. So here we can define a notion called active domain. Okay, so which has a very fancy name, but it's actually very simple, right? So the active domain of a query and a database instance is simply all the constant that you have in the query and in your database instance. Okay, and by definition, active domain is always finite because your query is of finite size, and also your database instance is finite. Okay, so after you define the notion of active domain, we can define alternative semantic for query Q, and we can simply constrain all the free variables to be in the active domain. They don't take all the possible value in the domain anymore. They actually take the value in the active domain. This is the alternative semantic for a query. Okay, and then you can do similar things for the quantifier, right? So you can just kind of scope them to the active domain instead of allowing them to take values in the whole domain. Okay, so it's actually very easy to see that relational calculus queries under this semantic will always give you a finite answer. Okay, if you think about why, first one, active domain is always finite because the query is finite and the database instance like it's finite, right? So that's actually make sure if you are taking this semantic for your query, you are never going to have any finite database instance give you an infinite answer. Okay. So now we talk about essentially two different query languages, right? Relational algebra, relational calculus. So let's look at their relationship. Okay. So let's put them side by side and try to understand what we have here. So let's talk about theory. Because kind of clean in that aspect. First one is very easy to see that relational calculus is more powerful than relational algebra. What do we mean by that? Precisely, right? We think about a query as a function that map a database instance to a relation instance. Right? And the query language is simply how powerful it is simply what type of functions that I can express in that query language. By saying relational calculus is more powerful than relational algebra, essentially what we are trying to say is there are queries that you are able to express in relational calculus, but you cannot express in relational algebra. Okay. So how can you prove that? Right? We are not going to go through this like in the lecture, right? But if you are interested in it, right? So you first prove all the queries in relational algebra can be expressed in relational calculus. How do you do that? You do one pass of like induction over the structure of relational algebra, and you can see it's pretty natural to prove it. So, and then you prove the other way around, right? You try to prove that there's some query in relational calculus that cannot be expressed in relational algebra. Okay, so this is also very easy to see, right? If you give me a relational algebra expression of finite size, it's always going to give you a finite answer, right? So if you look at all the operations that we talk about in relational algebra, none of them are going to give you infinite amount of tuple as a result, right? So however, on the other hand, we just look at one example in relational calculus that's going to give you an infinite amount of tuples in the answer, right? So clearly there are some functions that you are able to express in relational calculus, which are those unsafe queries, but you cannot express them in relational algebra if you are giving me a finite size input. And one very fundamental theorem in database back in 1970s is what people call Codd theorem. So that actually tells you, even though relational calculus in the original semantic is more powerful than relational algebra, if you take the domain independent relational calculus, using the active domain semantic we just talked about, it is actually as powerful as relational algebra, which is a very beautiful theorem. So how can you prove that, right? It's actually like you do the same exercise. You try to prove that relational algebra, all relational algebra expressions can be expressed in domain independent relational calculus, right? You do that by one pass of induction over the structure and you are done. Okay? And then how about the other way around, right? Other way around, you try to say, all the domain independent relational calculus query can be expressed as relational algebra expression. You can also do that by induction. Okay. And also from the system side, right? If you compare these two different languages, right? Relational calculus is declarative, as you can see, right? Whenever I'm writing this query, right? I'm not telling the database how to give me the answer. I mean, I have a three-way join here, but I don't know. I don't tell database you should join product with purchase first, or you should join customer and purchase first, right? So I don't tell the database how to run this. I tell the database declaratively, this is what I want. I want all the tuples that satisfy this condition. That's what we mean by relational calculus is declarative. On the other hand, relational algebra is imperative in the sense that the system can follow this step by step and give you the answer. It's going to first join product with purchase and then join with and then join with this relation and do the projection. Okay. So in database, the user is going to write in relational calculus because we want that to be declarative. And what system going to do, as we are going to see, is to automatically find the best relational algebra formula to really answer the query from the user. And because of Codd theorem, this is always possible because any single query you are writing in domain-independent relational calculus can be expressed as an expression in relational algebra. That's the beauty of this, okay? So now we talk about this essentially three different query languages, right? We talk about relational algebra and we talk about relational calculus, right? And clearly we can see that relational calculus is actually more powerful than relational algebra, right? And we talk about one alternative semantic of relational calculus queries that is equivalent in expressive power compared with relational algebra. And now let's talk about two other query languages that are less powerful than relational algebra and domain-independent relational calculus. And we talk about it because they actually form the foundation of the most popular type of queries you are going to write in a practical system. So the other type of queries that we call conjunctive queries. So why do we even need that? Right, so we have domain-independent relational calculus, which is great, right? So it's always safe, always give you a finite answer, and we like it. But even that, there are a lot of properties that's very hard to analyze for domain-independent relational calculus queries. And let me give you some examples. So assuming you give me a domain-independent relational calculus query phi, does there exist a database instance such that the output of this query is non-empty, right? So here essentially, if you want to understand the satisfiability of a domain-independent relational calculus query, it's actually not decidable, okay? Even though this query is safe, but answering this satisfiability query is also undecidable for such a query. And also, if you give me two domain-independent relational calculus query, phi1 and phi2, right? And if you want to say, are they equivalent? Meaning that, can we prove that no matter what database instance you give me, they are always equivalent. They're always going to give you the same answer. And answering this query, answering this question is also not decidable, right? So as you can see, right, even we constrain our semantic to have a query that's always safe. If you want to understand this set of really fundamental questions about the property of those queries, they are still really, really hard to do. So we can actually further constrain our query language such that checking these properties are easier. And we are going to look at one of such examples. And that example is something what we call conjunctive query, which actually constrain the type of formula you can pass in to the system. Essentially, for conjunctive query, I'm only allowing the formula of this form. Okay, that is I only kind of allowing all those formulas that is a conjunction of a whole bunch of items. Okay, so here's just one example. If you give me a relation professor with two attributes, professor ID and the name. If you give me another relation lecture with lecture ID, title, and professor ID who teaching the lecture. If you want to get all pairs of professor and lectures that this professor teaches that lecture, you can express it as a conjunctive query, look like this. Okay, so here is a free variable name and title, right? Name of the professor, title of the lecture, right? And then this is a conjunctive query formula, right? You can see it's a conjunction between the professor and the lecture, between these two items, right? So in conjunctive query, I'm only allowing formulas that look like this. I do not allow you to give me any fourth order logical formula anymore. I only allow this. Okay, so this gives you kind of a less powerful query language. So there are a lot of good and interesting property here. We are going to look at some example, but they will not be in exam, right? The exam will be very similar to last year. You can look at it, right? So this will not be in exam, but as someone who is learning database at ETH, I really believe you should know about this. So here are some really good properties. So one thing that's interesting is if you give me a conjunctive query, it is actually as expressive as relational algebra with only selection, projection, join, and renaming. It's actually pretty beautiful correspondence between anything that you can write in conjunctive query and also this subset of relational algebra expressions. So how to prove it? Well, I mean, you do that by induction, right? So you first prove that all this subset of relational algebra can be expressed in conjunctive query, and then you prove the other way around. That is, if you give me any conjunctive query, like a query, right? So I can express that using this subset of relational algebra. Okay. So the way to do it, we are not going to the detail, but the way to do it is you really try to establish the one-to-one correspondence between these two query languages. Okay, you put them side by side. So whenever I'm having a relation, right, conjunctive query, I have something like this, right? Whenever I'm having selection, having projection, having cross product, right? So essentially, there's actually one-to-one correspondence between what you can do in relational algebra and what you can write in conjunctive query. So once you put them side by side, it should be very natural for you to see how to prove it. Okay. So another property of conjunctive query is it is monotonic. So what do you mean by that? It's monotonic in the sense that if you give me two database instances, I1 and I2, and I2 is a superset of I1 in the sense that I2 contains more tuples, strictly like more tuples compared with I1. Okay. And then if you evaluate the same conjunctive query Q over I1 and I2, you can always prove the answer of that query over I1 is also going to be a subset of the answer of that query over I2. This is what we mean by monotonic. And it's actually very easy to prove. Okay, so how to prove it, right? So I have a conjunctive query look like this. So all I need to prove is that any tuple in the answer of QI1 is also being the answer of QI2. Okay, we are not going to go through this in detail, but if you are interested in this, right? So this is actually maybe like 5 lines of proof that you can actually write down, and then you can actually prove all the conjunctive queries are actually monotonic. So these are just some examples, right? So and you can see just one really concrete example about what you can do by constraining the syntax, right? So essentially, if you look at database theory, right, a large part of that is try to understand different type of kind of query languages and their correspondence, like their corresponding property. How hard is it to analyze that? And like how can we design efficient way to analyze that, right? And you can keep alternating the semantic, and you can keep alternating or constraining the syntax such that you can get a different collection of query languages that have different difficulty in analyzing different properties. Okay. So that's enough for theory. Okay, this is not a database theory course. If it's a database theory course, we can spend the whole semester talk about this. But this is not a database theory course. So let's move on to the practical side, because that is going to be our focus of this course. Now we talk about all those query languages in a very abstract way, right? Relational algebra, different flavor of relational calculus, right? So now we're going to talk about how to actually write them in a real database system. As we are going to see, there's a subset of SQL queries that have one-to-one correspondence to conjunctive query. Okay, that's going to be those queries that you are maybe most frequently like you are going to write in practice, and that's those queries only involving select, from, and where, as we are going to see. And then there's a subset of SQL queries that's corresponding to all the possible relational algebra expressions that you are going to that you are able to write in theory. And then, of course, as any practical query languages, there are going to be a small gap between theory and the practice, right? And you are able to, in the full SQL language, to write queries that goes beyond what we have been talking about so far. Okay, so this is going to be the structure of this lecture and also the next couple of lectures. Okay, so let's talk about the real world. Okay. So here we are going to talk about a practical query language called SQL. Okay. So before we start talk about the details, right? So first of all, we need to understand that we are learning a language, right? So like as you know from learning any languages, right? So learning from a lecture is probably the worst way of doing that, unfortunately, right? So the best way of learning a language is first one to practice, to really write real SQL queries. I don't really know kind of any other way to get around that. And second is to read some like references of the language, right? To really understand how to write something. Okay. And for practice, next week we are going to have 2 hands-on sessions in the lecture that we are going to write SQL query together. Okay. But it's very important that you actually like not only learning SQL on a piece of paper, right? But really write it right on your computer, right? And for reference, right? So there's actually chapter 6 of the Stanford book, right? You need to read it. There's no way you are going to learn SQL query by just watching this lecture. I hope I could cover all the details in the lecture, but that's simply not possible because we are learning a very complicated language. You need to read chapter 6 of the book, okay? And also in the lecture, the goal is not to cover all the details, right? So we want to give the structure about what we are going to talk about, right? But you really need to read the book to handle this language, and you really need to practice it, right? Like by yourself, okay? Okay, so let's talk about SQL, right? So before we talk about what SQL really are, right? So let's assume you are a researcher in the 1970s, right? You see these 2 very beautiful query languages, relational calculus, relational algebra, right? You want to build a system for that. How would you design it, right? So if you think about it, it's probably 3 different components in the system that we need to understand. So assuming you have database, a whole bunch of relations, right? You want the user to give you a query, you give the user another relation. How would you design a practical language for this? Well, I need to provide the user a way to define the schema of the relation, right? Otherwise, I don't know the shape of relation. I need to give the user some way to actually put information into the table, right? Otherwise, there's nothing I can query from, right? So after define the schema, I need to define the content, I need to load data into my database, right? And then I need to define the query language itself. So these 3 components is actually 3 different kind of like components like in the query language. We are going to talk about how to define schemas and also how to put information into a table and also how to query it. Okay, so that's the structure. So if you think about SQL queries, is actually a family of standards. Okay, so it has one substandard called data definition language, right, which is corresponding to component number 1 to try to define the schema. It has another component called the data manipulation language to try to put information into the table or update information or change information, right? So, and also it has the 3rd component, which is the query language. And we are going to go through them one by one, but this is the structure, okay? And a little bit of history of SQL, right? So it's actually the first defined by a paper in 1974. It's actually doesn't, the name was not SQL, it's actually called like really SQL, right? SEQL, right? So that's the name. If you're interested, you can actually read this paper. But then it changed the name to SQL, right? So there are different debates about how to pronounce it, right? But yeah, that's a different story. So it's a standard that kind of keep getting in, like ever evolving kind of standard, right? So the first standard, like SQL 2 is like SQL 92, right? So it define what is join, what's auto join, all those type of things. And in 1999, there's SQL 3 to define a whole bunch of different functionalities. Right, in 2006, you can actually do that. Like you can do SQL like XML in the standard, right? So and then the whole bunch of different standards. Okay. So and then the whole bunch of like relational database systems that support some flavor of the standard. Okay. So as you are going to see, right? So different database engines have actually different implementations that kind of slightly different from the SQL standard in a very unique way, okay? So, and also different database engines may have different extensions of the language, okay? That are unique, like to that database engine. So in this course, we are going to use PostgreSQL as our reference, okay? But when you go to the real world, right? When you are doing your job, right, or doing your projects, or you are using a different database engine, just to make sure that you understand the same SQL query that you are writing for PostgreSQL might not always work for other type of database systems, okay? It's simply because SQL is a standard and different systems implement a different flavor of that standard. That's very important. Okay, so another thing that we need to keep in mind before we go to the language is that we talk about relational calculus and relational algebra, right? So everything that we introduce on the theory side, we only talk about the set semantic, okay? But in reality, in SQL, and we are doing that in practice, a relation is a bag of examples, okay? So and also in the exam, whenever we are talking about relational calculus, relational algebra, it's always a set because that makes our life so much easier, okay? And whenever you are deal with a real system, right? That's a bag semantic, okay? Okay, so now let's talk about different components of the queries of the SQL standard. So the first component is the data definition language, DDL. So the goal of that is really try to give you a whole bunch of ways that you can define the schema, okay? So let's recall theoretically, right? On the theory side, a schema looks like this. It has a name of the relation. It has a whole bunch of attributes of the relation. And for each attribute, you have the domain, okay? So if you are designing a language, you are probably going to reach the same conclusion, right? So in SQL, if you want to do that in practice, I need to give you one way to specify the name, specify a list of attributes, and also the domain for each attribute, okay? So this is the syntax that the system can support, right? If you want to create a relation, right, you can have write down like create a table, right? And then this is the name of the relation, right? And then you can list out all of the attributes. You have the like personnel number with the type integer, right? You have the second column like which is name, and you have this, right, as a type. You have a level, right? So something like this, right? Like any like kind of programming language, SQL also give you a predefined collection of data type that you can use. And also you need to define your primary key, right? The way to do it is by have this keyword primary key followed by the set of attributes that act as the primary key, okay? So here, essentially, we say, so the primary key of this relation is a personnel number, okay? If you give the system this kind of statement, it's going to create a relation called a professor with this schema, Okay, so this is essentially what you are trying to do, how you bridge the practice and the theory. Okay, we talk about on the theory side what is the schema is, right? So to define it, this is the statement that you are going to write. So, and you can delete a relation, right? Once you create a relation, you can delete it. So the way to do it is you say drop table professor. Okay, so you are going to remove this relation from your database. And you can modify the structure of a relation. Okay, you can add a column or attributes, right? So for example, you can say alter table professor, add column, and you say this is the name of the new column, which is H, and then the type is integer. Okay, it's as simple as that. So there's one question that's interesting. That is, I mean, not have a relation, I fill in a whole bunch of content, I run this statement to add a new column or attribute. What is the value that database should fill in for that new column, right? After I run this statement. So that actually depends. In many cases, you can set a default value for this column. That is, if I do not specify what the value is, database is always going to fill in that default value. And if you do not specify default value, the database is going to keep that empty. Okay, essentially that's the way a database is going to tell you, okay, I do not know about that, like the value of that cell or that column. So that might sound very simple, but as you are going to see on Friday, is actually have a very delicate semantic about what do we mean by something being empty. Okay, so that's something we are going to talk about on Friday. So of course you can delete a column, right? You can alter table professor with the name of the relation. You can drop column, right? And put the name of the column, right? And then you are going to have a relation without that column, right? So it's as simple as that, right? So and there are more. There are so many different ways you can alter kind of like structure of the table, right? Like again, the best way of learning that is read a book, and more importantly, when you actually use that functionality, Google it. Okay, I hope I have a better way for you to learn language, but I do not have that. Okay, read a book, practice. Whenever you need some functionality, just Google it. Okay, for example, if you want to say, how to add a column in in a relation, right? Just open Google, SQL, add a column, you are going to get that. Okay. So let's look at this example. This is a university database that we have been working on for a while now, right? So it has information about professor, student lecture, so on and so forth. How can we specify this schema using SQL queries, right? So for example, here, right, if you want to specify the professor relation, right, I create a table professor with 4 different attributes, personnel number with a type integer, so on and so forth. And I say primary key is personnel number, right? After you issue this statement to the database is going to create that relation for you. Okay. And similarly, this is for students, right? So it's very similar to the professor relation. For lecture, it's also very similar. It gets a little bit interesting if you specify the requires relation. So here I create table requires with 2 attributes, prerequisite and follow-up. And as we mentioned in the last lecture, right? So a natural choice of primary key for this relation is the combination of prerequisite and follow-up, because that would allow us to have the cases that one course is a prerequisite of multiple courses and the other way around. Okay, if you have multiple columns as a combination of the primary key, right? So one way to write it is to have primary key, right, and you put them together here. Okay, that's an interesting part. You can write that for tens, right? You can write that for tests, right? So this is actually a practical way for to specify the schema that we talked about in the last lecture. So now we have the schema, okay? We have the shape of the relation. We have the header of the relation. Now it's time for us to put information into those relations before we can query it. And the subset of language that we are going to talk about is data manipulation language, which is actually try to put information into, try to put like information into a relation, also try to manipulate those information. For example, if you want to put something into a relation, right, you can have a statement called insert into, right? So here you insert into the relation student, right? You want to put information into these two columns, personnel number and the name, right? And the value you want to put in is personnel number equals to this, name equals to this, right? So if you run this, right, you are going to have a new row in this relation with personnel number equals to 28121, with name equal to 3, right? What would the database put for semester? Because you are not specifying it. It's either the default value or it's going to keep it empty. Okay. Next semester, we are in the next lecture, we are going to talk really precisely what we mean by making it like it empty. Okay. Right now, just think about, yeah, it's a cell. The data say you don't specify it. I don't know the answer. Right. And you can delete kind of tuples from a relation. For example, if your issue a query look like this, delete student where semester larger than 13, right? It's simply going to remove all the examples, all the tuples in the relation, like whose semester value is larger than 13, right? You can actually update the information in the relation. You can update students that semester equals semester plus 1, right? What's going to do is going to increase the semester value for all the examples in the student table by 1. It's very natural, right? So we are not going to the full specification of the language in the lecture. Please read the book. Okay, it's very important to read the book. And in general, when you are dealing with kind of real-world database systems, right? So to populate the information in a database, it's a process that we often call ETL, right? So it's extract, transform, and load, right? So that's actually like the thing you need to do before you can write any queries, right? Because I need data in my database for me to query, right? So it could be done in multiple ways, right? You could populate the database tuple by tuple by just keep writing the insert into statement for every single tuple you have. The problem is that it's often going to be very slow, right? And then there's a whole bunch of automatic tools for you to do that. For you to kind of get data from some file, right, and do the transformation, right, and also insert that into a database as a whole, right? So in reality, ETL is a very large collection of tools that you can use. So here's just like some very simple examples, right? So assuming I want to put this relation, the content of this relation, the 3 tuples, into my database. So there are multiple ways that you can do it. You can do that tuple by tuple, which by just issuing these 3 different statements, you keep doing insert 3 times, right? Every single time you run it, database is going to insert 1 tuple. You keep doing that 3 times, you're done. Okay? So the problem of this is it could be slow. And there are actually 2 fundamental reasons behind why it is going to be slow. The first one is whenever you are issuing this query, the database need to parse the query and try to decide how to run this query for you. And because you are issuing this query independently, the database is going to do that parsing step and the optimization step independently multiple times. And that could be very slow. And second is that whenever you are updating the relation in a database, you need to check whether it satisfies all the constraints that you have on your data. For example, if I have a personnel number as a primary key, every single time I'm inserting a new example, a new tuple, the database is going to check whether you introduce duplicates for the primary key, right? So if you are doing this 1 by 1 per tuple, the database need to check the key constraint every single time that you have any updates in your relation. And in practice, that's often the more fundamental reason that why doing kind of data loading tuple by tuple is often not the best idea in the world. So how can you do that, right? So in many of the real world database systems, it often gives you a way to load a whole bunch of data at once. So in PostgreSQL, you can actually do this. You can copy professor, which is relation database, from, for example, the CSV file, right, with kind of some description of the format, right, such that the database knows how to deal with it. If you do this and you put all the information in that CSV file, the database is going to load the whole thing at once and only checking the key constraint once. Okay. So another thing that's interesting is there are interactions between the between DDL and DML. Okay, and especially when we are updating the relations and some of that violate the key constraint. So let's look at one example here. Okay, so on one hand, let's make that larger. Okay. On one hand, you have the DDL. That is, you create a table R, which is going to give you a new relation with two attributes. The first attribute is called A, the second attribute is called B. The first attribute A has the type integer. The second attribute B has the type integer, and your primary key is the attribute A. Okay, you can build a schema, and now I have a database with this relation. And what if I want to insert examples into my database, right? So here you are inserting some example with a value 0, 1, A equals 0, B equals 1 into R. It's one statement. You can do that second time. You can insert another tuple with value 0 and 4. As we can see, the third time you are issuing this query, you are going to violate the key constraint, right? Because you are introducing a new tuple that shares the same value on the primary key as the first tuple. So what would happen? We'll really run these three different queries. Your first two queries are going to be fine. Okay, so the database will not complain about that. After running the first query, you have a table with one tuple. After you run the second query, you have a table with two tuples. The moment you run the third tuple, you are going to get an error. The error message is actually a function of the database system you are using, but they are going to tell you, okay, there's actually a duplicate key value violating the unique constraint, which just means that you are inserting a new tuple that shares the same value on the primary key as like with another kind of existing tuple. Okay, so there's this type of interaction between DDL and DML. And as a user of the database system, whenever you are updating the relation, the system is going to automatically check whether all the constraints you are specifying in DDL is getting violated or not. If it's getting violated, it's going to throw an error. Okay. Okay, so that's all we have for today, right? We talk about relational algebra, relational calculus, different type of query languages, and then we start to go a little bit into the real world, and we talk about DDL and DML in SQL, how to design the schema, how to put data into a database. In the next lecture, we are going to talk about something that is really interesting, that is how to query the data you just put into the database to get the insight you want for your application. Okay, so that's all for today. I'll be here to answer whatever question you have. Otherwise, I'll see you guys on Friday. Okay. Okay, so any questions, just speak up. Yeah.
Yeah, I have a question about the active domain, domain independent. I didn't quite catch what is going on there. So we say the active domain is defined as all constants in Q and I. So what are the constants in Q and what are the constants in I? So from my understanding, So the constants in I, from my understandings, are just like everything that is in our database, right?
Yeah, so constant in I is everything in your database instance. Yes, yeah.
Right, and what is then the constants in the query?
Oh, for example, I have a query with, for example, I want to find all the students whose name is whose name is Anna, right? Mm-hmm. So and Anna is a constant because you are going to have sub-selection, right? So mm-hmm. like that's all the constants you are using in your predicate.
Okay, and then the semantics, can you quickly explain like what the semantics point you want to actually convey? Because I didn't quite catch that.
Yeah, so like essentially, right? So if you do not have active domain, right? So all those free variables can take value in the domain, right? And that's infinite. Here I want to say, okay, you cannot take all the values. You can only take those values that exist in the database and the query.
Okay. That clears it up. Thank you very much.
Right? Like for example, I have a table called animal. I know there's only 3 types of animals: dog, cat, elephant. I want you to assume that's all the animals.
Okay.
There's no other type of animal that I don't know, because otherwise you are going to output a whole bunch of those, right?
Okay.
So
yeah,
that's a fundamental thing we try to make sure in this. Yeah.
Thanks.
Yeah. Cool. Yeah. So I think we have more questions. Yeah, just go ahead. Just unmute yourself and speak up.
Okay, I have a short question about the bag semantics of a database. And what I wanted to ask is, bag semantics allow for the same entry to be inserted twice, right? But then the
assuming
key would
you,
obviously
assuming they are not. Okay, so you cannot insert the same tuple twice if you have a primary key and they share the same value. Right? Yeah.
But when does bag semantics come into play then?
Oh yeah. So okay. So so it's better that if you look at examples. Okay. So let's look at this example. Okay. So I have relation R. So you can see my screen, right?
Yes.
Okay. I have 2 attributes A and B. My primary key is A. Okay. I build a schema. So if I do this, this will fail the second time. Okay. Right. So it's in a second. I'm not sure whether we actually right or not. Somehow breaks. Yeah, this website always breaks in the most perfect time. Okay, so I build the schema. Okay. Anyway, yeah. So what would happen is in SQL you can actually create a table like this. Create table R with A integer and B integer, something like this, without defining the primary key. If you do this, you are able to insert the same tuple twice.
Okay, thank you. So only if there is no primary key defined, bag semantics really come into play. Otherwise, it's set semantics.
We cannot say set semantic because when you're doing the query processing, it's still bag semantic. For example,
okay.
if I projection obey the primary key and do the union, it's still bag, right?
Okay. I'll think about it more. Maybe I'll come back to the next lecture. Thank you very much.
Cool. Yeah.
Just to continue this point, but I think when we defined the key constraint, the constraint was the following: if the key is the same, the rest of the values have to be the same. But in the example you were trying to show, it was if we insert 0, 1 twice, right? We have 0, 1 and 0, 1. They both have the same primary key, but they also have they also share the rest of the values. So why would that not work?
Yeah, because value doesn't decide the entity itself, right? So, I mean, essentially, I can have 2 people have exactly the same property, have same age, same semester, same name, but still 2 people.
Okay, so it's really identifying the tuples, and it's not like if we cannot say like the definition we had saying the key constraint, like what I was trying to say, that's not enough. It's really we need to identify each tuple uniquely.
Exactly, because each tuple corresponding to one entity in the real world, right?
Okay.
So I want to identify that entity, right? So that's actually a key difference between set and bag that makes it a little bit complicated, right? When you talk about set, you never have that problem, but for bag, yes, you are doing that on the tuple level. That makes sense?
Thanks. Yeah.
Any other questions? Yeah, just speak up when you have questions.
I think I still didn't understand. So with the bag semantics, we don't need to define a key or a primary key, or
in SQL you don't have to. right? So that is the like one thing in practice, right? So when you define like a relation in a database system, in a real database system, you don't have to have that primary key like part, right? So like you are able to define. Oh, this website is always broken the most. Yeah, whenever I need this, it breaks.
But is this the only time that we don't so that we consider the back semantics when we don't have a primary key?
Oh no. So it's always back semantic. Okay. So like for example,
Okay.
you can have like you can create table R. If you do this, right? So you like you can do that in a database system without any problem. Okay.
Mm-hmm.
So and then you can actually insert value like this, like without any problem. Okay, so essentially here you are going to have like one relation with actually two examples, both of them are 0 and 1.
Mm-hmm.
Okay, this will not violate any constraint you have because you don't specify a constraint.
Mm-hmm.
Right. So and if you create a table that look like this, and if you do this again, and then this one will have error. Because inserting a second type will violate this constraint.
But this is only because we defined a primary key. In which
Yes.
case would the back semantics be different to the set semantics if we don't define a primary key?
One example would be, right? So for example, I have two relations, right? I have relation 1 with one example like 0, 1, okay? And I have relation 2 with another example 0, 1, okay? The same thing, okay? And then in SQL, like down the road, you can do the union between 1 and 2, okay? This one will give you a relation with 2 tuples, not 1. That's another example about why it's a back, not a side. Yeah.
Okay.
So the primary key thing is, you're right. So that's one thing that you are seeing. That's the difference between back and side. But that's not the only difference. There are other differences.
Okay.
Yeah. So like
Thank
in
you.
SQL, if you do in SQL, if you do the union, you are going to get this. Yeah.
And then there will also be no primary key, right?
In this case, there's no primary key if you do not specify it. Yeah, that's true. Yeah.
Yep. Okay.
Okay.
So could you maybe go back to the slide with relational model and more concepts? It's relatively at the beginning. I think it was a recap.
Yeah. Yeah.
No, it's the more concepts. That's the next one.
Okay. Oh, yeah. Cool.
Exactly. So the all valid instances, that was what I was referring to when I was talking before. Because now this says as soon, so if the keys are the same, that means the values are the same, right? Or am I misunderstanding this?
But this is a set.
But it's a set, so automatically it's okay. I mean, if we assume it's a set, and it makes sense. But other than that, I feel like that's maybe a bit weird. But maybe that's just me.
Oh no. So if it's a bag, then you cannot do this.
Okay. So it's really, we have to have a set. Okay.
Yeah. So like all the theory that we talk about, they assume underlying the cover is a set.
Okay.
Right.
Okay.
So if you really want to bag, the whole thing will become much longer than what we have. Yeah. So yeah.
Alternatively, we could have maybe written down some quantifiers that says that there exists no two tuples such that k and k prime are equal, right? That would be an alternative way to define all valid instances. Okay.
Yes. Yeah. That's true.
Okay. Thanks.
Can you maybe answer my question now? So how the hierarchical model would be implemented?
Oh, sure. Can you repeat your question? I kind of forget about that.
So in the first lecture, I think we had the three different models: hierarchical, network, and relational. And you had the slide where you were essentially drawing a tree with like yellow rectangles where there was ABB and then part 1, etc.
Yeah.
And my question is, what are the yellow rectangles standing for? So are these like objects, or are they
let me bring back the slides. You are talking about hierarchical model, this one, right?
Yeah, exactly.
Perfect. Okay, great. Yeah, so here, so it's a very good question. So essentially, like your question is essentially what are those like yellow boxes, right?
Yeah, is it a table or is it an entry?
It's an entry. It's actually one record on the hard drive.
Okay.
Right. So the ABB is one record, right? And then you actually store this record, and you have pointer, and you have So like each of the yellow box is a record.
And are they standing somewhere in a table, or is it really like how you would implement a tree, for example, in Java, that you are having an attribute saying next or sun, or I don't know?
Yeah. So so here we need to draw the line between theory and a real system, right? So at least in theory, when we talk about the hierarchical model, they are actually just like a tree, literally the tree. Yeah. So and we are using the real system like IMS. I'm sure there are other things go beyond this very simple theoretical model, but when you are talking about the theoretical model, I mean, it's literally the tree of record.
Okay. So so what would be an example to somewhere remember what your sons are? Because we learned, for example, that if you're creating a tree in a program, then when you pull out the electricity of the computer, the tree will get deleted because it's not in memory.
Yeah.
So we learned kind of that you only can have things in memory that are also like stationary there if you put it in tables. So I was a little confused how you could create a database that is not based on tables.
Oh, no. So like you are not going to like lose information as long as on hard drive, right? Doesn't matter how you organize it, right?
Okay.
Right. So okay. So let me find some. Yeah. So so the detailed implementation of hierarchical models goes way beyond what we are going to cover in the course. Because we will spend the whole course talk about relational model. But let me try to find for you some reading that you can you can do to know a little bit more about IMS and the hierarchical model.
Okay.
Okay. So here is just a very simple kind of at a really high level what this is. But let me try to find some detailed reading for you. That work? So can you send me an email to remind me, and then I can send that to you? Yeah.
Okay. Should I write you an email or?
Yeah. Email would be great. Otherwise, I'm sure. Yeah. The email would be great. Otherwise, I'm sure I'm going to forget.
Okay. Thank you very much. Have a nice day.
Yeah. Sure. You too. Okay. So any other questions? Okay. Otherwise, see you guys on Friday.